Okay, here are notes over parent functions, which a lot of these we've seen, a few are new. So for linear, our parent function is going to look like f of x equals x. Domain is the set of things that we can put in for x. If we look at our graph, we don't have any restrictions. We can put in any value of x and it'll be just fine. So our domain is going to be negative infinity, positive infinity. In the same way, the values of y that we can get out are going to go down here, negative infinity, all the way up here to positive infinity. Our range will also be negative infinity to positive infinity. Now, in general, for end behavior, we're usually going to do positive infinity here, negative infinity here. So as the x value, if we were to trace this on a graphing calculator, and remember for trace, we're going to hit either the right or the left. If we trace to the right and let x get bigger and bigger and bigger, the f of x, the y, is going to also approach positive infinity. And then if we trace to the left, as we get further and further negative here, this is going to get further and further negative in a y direction. So this is going to be negative infinity as well. It crosses the axis, both axes, conveniently here at 0, 0. So our x-intercept is at 0, 0, and our y-intercept is also at 0, 0. We're going to go through the same process 8 more times. For quadratic, quadratic is what we're used to seeing as x squared. Domain, there is no limit to what we can put in for x. We can do really big negative numbers, we could do 0, we could do really big positive numbers. So my domain is negative infinity to positive infinity. Pretend that that looks like a good infinity sign. The issue is that it doesn't matter what I put in, I'm never going to get a negative number out because of that square function. My range is not going to be infinity to infinity. Instead, my range, the y values that I can get out, I'm going to start with 0 and I'm going to include 0. So I'm going to use a bracket. I'm going to say 0 to positive infinity. So that means that I'm going to include 0 and it's going to include all the y values, increasingly positive and approaching infinity. End behavior, so as x goes to positive infinity, I'm going to keep going positive. And this is a little weird. As I go to negative infinity for x, my y values are also going to get increasingly positive. So instead of putting negative infinity here, I'm going to put positive infinity. Now my x-intercept, the place that I cross the x-axis here, is at 0, 0. That is also conveniently where I cross the y-axis. So both my x-intercept and my y-intercept are at 0, 0. For my absolute value function, remember this is where I'm using straight lines. And if I have a positive number for x, it's going to give me a positive number out. If I put in a negative, it strips off the negative and makes it positive. So there is no restriction on what I can put in for x. My domain will be negative infinity to positive infinity. My range, because I include 0 and only go positive, my range is going to look like that for quadratic. So I'm going to have 0 inclusive up to positive infinity. So that means that my end behavior is also going to be the same as quadratic. So that'll be infinity, positive infinity, and then as I try to approach negative infinity, my y is going to get increasingly positive, so that'll be positive infinity. I cross both axes at the origin, so that'll give me 0, 0 and 0, 0. Okay, cubic is next. Cubic is going to have a parent function that looks like x to the third, x cubed. There's no restriction on what I can put in for x. I can put anything in, so my domain is negative infinity to positive infinity. If I put in increasingly large values of x, I will get increasingly large values of y. Same thing here, if I put in increasingly smaller values of x, or increasingly negative values of x, I will get increasingly negative values. So that means that my range will be negative infinity to positive infinity. And things are going to look an awful lot like that linear page. So my end behavior will be positive infinity, positive infinity. As I go increasingly negative, I will also go increasingly negative in the y. And I cross both axes at 0, 0 and 0, 0. Okay, square root. Things are going to get interesting with square root. So this is also called a radical function. And it looks like the square root of x. Now, I have a restriction on what I can put in for x. I can't do this for negative numbers, but I can do it for 0. So my domain is going to include 0 and is going to go to positive infinity. And my range, the y's that I can get out, the smallest y I can get out is 0. But it will get increasingly bigger as I make my x bigger and bigger. So this is to positive infinity. So for my end behavior, as I approach positive infinity, I'm going to get increasingly positive. But as I approach 0, my y is also going to approach 0. And then I do have this convenient intercept here where I cross the x, or actually I hit the x-axis at 0, 0, and I hit the y-axis at 0, 0. So that's a little bit different from what we've seen so far. And a cubed root is going to look like this, but with a little 3 that sits right there. Now, if I look at my graph, there are no restrictions on what I can put in for x. I can put in negative numbers, I can put in 0, I can put in positive numbers. My domain is negative infinity to positive infinity. And it looks kind of narrow, and you'll have to take my word for it, but as I go increasingly in a positive direction, my y value is going to keep getting higher and higher. So that means that my range is also going to be negative infinity to positive infinity. This makes it easy to fill out my end behavior. Positive infinity is going to go to positive infinity, and then negative infinity to negative infinity. My x-intercept and my y-intercept, I cross my axes conveniently at this point here. So I'm going to have 0, 0 and 0, 0. And that is cubed root. Okay. These are the 3 new functions. So we've got exponential, logarithmic, and reciprocal. Exponential is going to have the variable in a different place than we're used to seeing. So I'm actually going to write this as b to the x, where b is going to be greater than 0. That's what this exponential function is going to look like. We're going to have some number here, like 2 or 3, or 1/2. The only key thing is that this has to be bigger than 0. Not x, but this base thing. So my domain, I can put anything in for x. There are no restrictions on what I can put in for x. My domain is going to be negative infinity to positive infinity. My range, if I look at this, I actually have an asymptote right here. I have an asymptote on the x-axis. And so that means that I don't care how negative I get in the x direction, it's never going to hit, touch, or cross over 0. That means that my range is not going to include 0, but will go up to positive infinity. Now for end behavior, remember this is x. X can go to positive infinity, x can go to negative infinity. And as I go to positive infinity, my y is going to go to positive infinity. As my x goes to negative infinity, my y is going to get increasingly closer and closer to 0. So that's what my end behavior will look like. I never actually crossed the x-intercept, or sorry, I never actually crossed the x-axis. So I'm going to say this does not exist for my x-intercept, but my y-intercept right here is actually going to be at the point 0, 1. So that's a little bit different, and now I have a place for an asymptote. Well, my asymptote here is going to be at y equals 0, which is going to make it a horizontal asymptote. Now, logarithms are in some ways kind of like the reverse of an exponential function. A log we are going to actually write as log x. As we can see from here, I have an which means I have a hard limit on what I can use for x. X has to be positive. X can't be 0, otherwise I wouldn't have this asymptote here. So my domain is going to be 0 to infinity. But as you can see from my range, or for my graph, there's no limit to how low that y value could go. And there's not going to be a limit on how high that positive y value can go either. So my range is going to be from negative infinity to positive infinity, which means that my end behavior as x approaches positive infinity, y is also going to approach positive infinity. And then I'm going to use a little bit of a weird symbol. I'm going to say as x approaches 0 from the right side, that's what that plus means, my y is going to approach negative infinity. Now I cross an x-axis at the point 1, 0, but I never actually hit or touch the y-axis. So I'm going to say that this guy does not exist. And I have an asymptote at x equals 0. Okay, one left. Reciprocal, sometimes we call this an inverse function. We're going to say f of x equals 1 over x. Sorry, that's a little squished. And I'm going to use a funny symbol that means union. So I need to find a way to exclude 0, because I can tell from these asymptotes here, there and there, that I can't let x ever be 0. I can also tell that I will never be able to get y equals 0. So that means that my domain, I need to find a way to express those exclusions. So I'm going to write negative infinity, not including 0, and I'm going to unite that domain with the domain of 0 to infinity. So that is actually a logic symbol that means union. And then I'm going to go ahead and do my range, which will look similar, actually identical. So as x approaches infinity, so as I keep going off this way, my y value is going to get closer and closer to 0. In the same way, as I keep getting more and more and more negative, my y value is also going to approach 0. I never cross the x-axis, I never cross the y-axis, but I am going to have asymptotes at both x equals 0 and at y equals 0.